Let me see what I have. Okay, so in the last lecture, we have introduced the first actually these several steps. The first two steps are the material selections and also the design of the aggregate structure for the SUPERPAVE mix design. And for the aggregate structure design, we also need to think about the preparation of the samples, where we will have to use the compaction. And there's one specific protocol for us to prepare the compacted specimen in SUPERPAVE mix design, which is called the gyratory compaction test. And the purpose of this one is trying to establish different trials of the asphalt binder contents. And then we will try to identify the properties of each trial. And also we need to blend the asphalt binder with the aggregate we select from the previous, from the first step. And then in the gyratory compaction test, we have initial number of the gyratory compaction and the designed number. And we will try to measure the properties of the specimen at these two points. And then using these 2 points to identify what's the whether this specimen or whether this trial is appropriate or not. So this is the general procedure for us to conduct the gyratory compaction test. And I guess there was something I pre-recorded. Just give me several seconds. Let me try to delete it. And okay, I think that's good. There are some standards for us to prepare the sample for the SUPERPAVE mix design. We have some specific requirement about the specimen's height and the weight. Usually for the mix design, we want the height to be around 115 millimeters, and with that, the weight of the sample will be 4.7 kilogram. And if we want for the moisture sensitivity analysis, the height is set around 95 millimeters, and where the weight is only 3.5 kilogram. If we are considering some loose specimen, in order to identify the maximum specific gravity, then we need to we need to determine the sample size based on the NMAS, which will be the nominal maximum aggregate size. We have defined the definitions of NMAS in the previous lecture. You can go back to check how it's defined. So if the nominal maximum size is around 19 millimeters, then the sample, the weight of the sample should be around 2 kilogram. If the size is around 12.5 millimeters, then we will only choose a sample with 1.5 kilogram. So this is the selections, the criteria for us to identify the amount of the sample we have to use to prepare the specimen. And what with that, in the actual experiment, we have to record everything. We need to have a batch of the samples for each trial. Like we have the trial 1, we have several samples. We have trial 2, we have trial 3. And for each trial, there will be multiple samples. And the reason for us to choose multiple samples is because we want to do some further analysis in the next step about the asphalt binder selection. But for this, for the second step, the aggregate structure design, we just need to identify those trials based on the gradation that we have specified in the previous lecture. And then we will mix the aggregates with the asphalt binder. We'll try to put them together and then blend them to make sure that the aggregate particles is covered with the asphalt binder. And after that, we will need to check the aging effect. Actually, we want to check the short-term aging effect. The sample will be placed in the oven for 2 hours at the compaction temperature. And once it's done, after 2 hours, usually if we go to the demo, we have already prepared this sample. So what you're going to see is that we're going to take the sample out of the oven and then put to the mold. And then the next thing will be very simple. We will put this sample, put the mold in the SUPERPAVE gyratory compaction machine, and then do the compaction. And the purpose of the compaction is we actually apply the load to the specimen, and then also rotate the specimen with a given number of with some designed numbers. And the purpose of this kind of compaction is trying to reproduce the field densification to which will be caused by the traffic and also the climate. So we will try to model this or simulate this situation in the lab. And also we will try to evaluate the property of the specimen in the lab. With that, we can try to by carefully selecting the appropriate trial, we can then accommodate the larger aggregates, and then are going to measure the compatibility of the specimen and also conduct some quality control to ensure that the one we choose is appropriate for the region where we're going to conduct the pavement or where we're going to design the pavement structure. And in the SUPERPAVE gyratory compaction, we're going to use the Texas equipment and also try to measure the French operational characteristics. Usually the specimen is put in the mold with the diameter of 150 millimeters, and this one can actually measure the aggregates with up to 37.5 millimeter nominal size. It's a very large aggregates. And during the experiment, we will try to record the height of the specimen to see how the height is changing over the time by the applied load. Usually we set this one as 500 kilopascal, and also by a given number of the rotations under the angle of 1.25 degree. And after the in the experiment, we will also have the control. The machine will have the control board for us to control the number of the rotations, and we also can use this control board to collect the data from the machine. And the data is recorded in real time. And we also have the outside will be the and a reaction frame, and also the mold will be put inside, and there is a loading arm and the rotation base so that we can rotate the specimen over the as many times as possible. And this would be the result from the gyratory compaction test. After the gyratory compaction, you can see the changes of the GMM, which would be the maximum specific gravity, and this one's related to the weight, to the height of the specimen, and is directly measure the density of the specimen. And the x-axis shows the number of the gyrations, with the number of the rotations you will do. So with more gyrations, the density of the specimen would be higher. What you're going to observe is like the linear increase about the density with respect to the log of the gyrations for the compaction. So this is the one we observed from the gyratory compaction test. And for different type of the in the SUPERPAVE mix design, for different type of the traffic, we will actually have different number of the gyratations. And also we need to identify two values. One is the initial, the other one is the design number of the gyratations. So if the traffic is less than 0.3 million equivalent single axle load over the design year, then the initial gyratation is 3 and the design value is 50. But with the increase of the traffic, like from 0.3 to 3 to 30 to more than 30, then you have to increase the number of the initial gyratations, the number of the designed gyratations to represent the dense traffic, the high traffic applied to the pavement structure. So for the traffic is higher than 30 million over the design life, then the initial is 9 and the design would be 125. So in the design of the SUPERPAVE mixed design, there will be some requirements. Actually there will be some variables we have to measure during the experiment. One is the specimen's height, which is related for the estimation of GMM, the maximum specific gravity. And also there will be some mixture volumetrics, including the air voids, the voids in the mineral aggregates VMA, and the voids filled with the asphalt. There will be more detailed definitions about those variables in the tutorial 3. So if we want to see how these variables are defined, you can go back to check the slides and the video for the tutorial 3. In addition, we are also care about the dust proportion, which will represent the percentage of the fine particles in the design aggregate in the design specimen. And also we want to measure the GMM at the initial gyratation. So with that from the experiment, you can collect all these informations. For each trial, you will be able to know what's the trial binder content we set. Usually we will set the same amount of the trial the binder contents, the asphalt content. At the trial step, we will just use 4.4%, and then we're gonna measure the GMM at the initial and the design gyratations. This will be measured during the experiment, and we also will measure the air voids, the VMA and VFA, and the dust proportions. So this would be the raw data we collect from the gyratory compaction test. And after that, we want to do further estimation about the volumetrics. The first thing we want to estimate is the estimated designed asphalt content at 4% air voids. The reason for us to choose the 4% air voids is like we don't want the air voids to be too high or too small. If the air voids is too high, then this mixture design will not resist to the rotting. But if it's too small, then the permeability of the pavement, the specimen will be very low, and with that there will be some issues about the impact from the moisture contents. So with this by using the observed data from the test, we can then estimate the design asphalt content, which will be in the function of the asphalt content in the trial blend, and the also the percentage of the air void VA. And this is the first part we want to estimate. The next one we want to estimate is the VMA, which would be the VMA at the designed asphalt content. And also in the experiment, we can find out the VMA from the trial blend, and this one will be determined by the initial value, VMAE, the estimated value will be determined by the initial value with respect to the air voids. And here C is the constant. It will be 0.1 when air void is less than 4%, and it's 0.2 when air void is higher than 4%. So we're going to use these two equations to calculate the estimated designed asphalt content and the estimated VMA at the designed asphalt content. So with that, I'm going to show you a simple example about how we're going to use these two equations. First, for the designed asphalt content, if we go to check the trial 1, the air void is 3.8%, and the binder contents in the trial would be 4.4%. So for the designed asphalt content, the value is the initial asphalt content minus 0.4 times 4 minus VA. Well, for the first trial, you can see that the PBI, which is 4.4, minus 0.4 times 4 minus the air void is 3.8. So with that, you can get the value as 4.3. So we can see that the for the designed binder content for the first trial, that will be 4.3. You can apply the similar procedure to calculate the other two trials. For the trial 2, that will be 4.5, and for trial 3, that will be 4.7. So this is the first one. We need to find out the designed asphalt binder contents for each trial. And the next thing we need to do is to find out the estimated VMA at the designed asphalt binder. So which would be VMAE, and we know that VMAE is a function of the initial value, which would be the value observed from the compaction test. VMI plus C times 4 minus VA. So if we go to see the first trial, VMAI is 12.7, and C is the constant. In the previous page, if the air void is less than 4%, C is 0.0. If it's higher than 4%, that will be 0.2. So in this case, the air void is less than 4%, so it's 0.0 times 4 minus 3.8, which will give you the value as 4.7. So it means that the estimated VMA is still 4.7%, and you can apply the similar procedure for the trial 2 and trial 3. That is, trial 2 is still 13%, and trial 3 is a little bit different. It's 13.3%. So that will be the two values we have to use for the next step of the asphalt binder selection. So with the calculation of those values, we will then can find out the volumetric design criteria of the SUPERPAVE. There will be some criteria about the SGC SUPERPAVE gyratory compaction test criterion. This one is applied to identify the GMM, the maximum specific gravity. We have some requirements at the initial gyrations and design gyrations. For the design gyrations, we want the value to be 96% for all different traffic conditions. But for the initial conditions, there will be some difference. If the traffic is less than 0.3, the GMM will be less than must be less than 91.5. If it's between 0.3 and 3, then that should be around should be less than 90.5. And if it's higher than 3, then the traffic is higher than 3 million, then the value should be less than 89. And so that's for the criteria of the GMM. We also have some criteria of the VMA, but there will be more details shown in the next page. And we have some requirement about the VFA and the dust proportion. So for the VFA, if it's also related to the traffic conditions, if the traffic is less than 0.3, that will be between 70 to 80. If it's less than 3, that will be 65 to 78. If it's higher than 3, that will be 65 to 75. And for the dust proportion, as a we have a specific range. It should be between 0.6 and 1.2 for the for all different traffic conditions. And with that, we can then go to check the performance of the performance of the 3 trials, and we do some calculation about estimating the asphalt binder contents. This would be the designed asphalt binder contents, and this is the VMAE. So what we can find that is for the asphalt binder, we will be estimate them as 4.3 for trial 1, 4.5 for trial 2, and 4.7 for trial 3. And we can then find out the GMM value at the initial. One is 86.9, 2 is 85.9, 3 is 87.9. They are all smaller than 89%. So all these 3 should be fine. And for the air void, we have do the correction, and they were all changed from the original value to 4%. And then we have the VMA, the estimated VMA. Trial 1 is 12.7, trial 2 is 13, trial 3 is 13.3. But we want for the VMA, the value should be higher than 13%. So in that sense, the first one, this trial, as it's less than 13%, so it's not appropriate. And this means that we should not use the trial 1 in the SUPERPAVE mix design. And for VFA, it's between 65 to 75, and you can see that all the trials satisfy this condition. And for the dust proportion, it's between 0.6 and 1.2. Also, they are satisfied. So with that, we can claim that the trial 2 and trial 3 will be the appropriate or be the candidate aggregate structure that we can use for the SUPERPAVE mix design. But if we are not lucky during the test, you find that none of the 3 trials are acceptable, then you have to recombine the aggregates to form more trials, and then try to test their performance, or you need to obtain new materials. And with that, you can get a brand new design for the specimen. So with that, we will complete the second step about the design of the aggregate structure. Do you have any questions so far about this design? Okay, if no, then I would just go to the next lecture about to continue the introduction of the SUPERPAVE mix design. And we have already finished the first two steps, the material selection and the aggregate structure design. And the third step is the design of the asphalt binder. We have to identify how much asphalt binder we have to select for the SUPERPAVE mix design. And this will also be combined with the performance grade we selected previously. So let's go to see more details about it. So the So in the third step, they selected the trial blend. From the second step will be the design aggregate structure that we're going to use. And then we're going to batch mix and compact more samples with this gradation. Usually we will prepare four samples, and each one will have different asphalt contents. And then we will determine the volumetric property of the four samples, and we will select the asphalt contents at 4% of the air voids and check the other volumetric properties. And then we also have the criteria about those volumetric properties. With that, we can then identify which sample with the specific asphalt content will be the most appropriate one to satisfy our requirement. So let's go to see more details. So first, we need to select the design different samples. For example, we have, like you can see that in the trial one, we have 4 samples, and the asphalt binder will be 3.8%, 4.3%, 4.5%, and 5.3%. Also, we have the trial 2. If trial 2 is also appropriate, we have the same amount of the asphalt binder, 3.8, 4.3, 4.8, 4.5, and this also applies for the trial 3. We have some. We marked each sample so that in the future you know what happens. So we prepare the samples for each trial, for each candidate trial, and then we're gonna measure their properties. Do the gyratory compaction test. We measure the GMM at the initial and designed gyrations. We measure the air voids, the VMA and VFA and dust proportion. Here you can see that the by increasing the binder contents, the air voids will be reduced dramatically, and this is one important feature we have to consider. So this figure actually shows the performance of the densification, which would be the value of GMM, under different number of the gyrations with respect to four different asphalt contents. And basically all satisfy the trend, like by increasing the gyrations, the value of GMM would be higher. But usually by increasing, if we increase the asphalt contents, the clearly you will observe the increase of the GMM, which will represent the density of the sample. So this is the general feature of the of all different design aggregate structures. And the next thing we care about is the what kind of asphalt binder we should select. As we defined previously, we want to select the asphalt binder at 4% of the air voids, especially at the design gyration, regardless of the traffic level. So so this 4 points is the one it's the value we obtained from the experiment, gyratory compaction experiment. And then we will try to do a linear regression to find out the relationship between the air void. The vertical axis is the air void, which is a VA. With respect to the percentage of the asphalt binder, and clearly you can see that at the 4% air void, the asphalt binder is 4.7%. So this is the one we have to select. It means that we need to select the asphalt binder PB at 4.7% from this relationship. And then we're gonna need to need to check more details. Usually for the VMA, the air voids with respect to the mineral aggregates, we have some specific requirement. That requirement is related to the nominal maximum size. If the nominal maximum size is 9.5, then we must have the minimum VMA of 18%. And if the size increase, as what you can see here, from 9.5% to 37.5%, then this minimum VMA value should be decreased. For the nominal maximum size of 37.5 millimeters, the minimum VMA should be around 11%. So those will be the criteria we're going to use to identify the asphalt binder. And for the mixed from the experiment, we actually can get the VMA. This is the VMA and the different asphalt binder. Again, we're going to use a line to fit to this curve, and you can find out in the concave relationship. It's a convex relationship, and we have already selected the asphalt binder at the asphalt content as 4.7%. So with that, we can then identify the from the x-axis, we can identify the VMA at 13.2%. So that's the selections about or the estimation of VMA, which is 13.2% for this for the blend 3 in this example. And for the VFA, the air void filled with the asphalt contents. This one is actually related to the traffic conditions. So we usually categorize traffic condition into 3 levels: less than 0.3, 1 to 3, and higher than 3. For the lowest level, it should be between 70 to 80. For the medium level, 65 to 78. For the high level, 65 to 75. This is actually the same to what we specified in the second step about the aggregate structure design. And you can also find out the data from the gyratory compaction test. We have the result. We have those yellow points, which will be the result from the experiment, and we use a line to fit to this all these 4 points. And we know that the designed asphalt content is 4.7, and with that we can then find out the VFA. In this case, VFA will be 70%. So that's for the VFA requirement. We will identify the VFA value from the test. And the next one is the dust proportion. And this one is the dust proportion is defined as the weight of the particles with the size less than 0.075 millimeters, and over the weight of the effective asphalt, which would be the unabsorbed asphalt. There will be some asphalt which will be absorbed by the particles, but for this part, for the part below, you will only refer to the unabsorbed asphalt, which would be the asphalt coated outside of the particles. So we want this dust proportion falls in the range of 0.6 and 1.2. And of course, from the experiment, we can find out the dust proportion of all the 4 samples. And we also need to have the line to feed to the data, to fit the relationship between the dust proportion and asphalt binder. And we select the asphalt binder as 4.7%, which will give you the dust proportion of, so dp will be 0.9 in this case. So with that, we have the dust proportion of the blend 3, the sample 3. And the next thing we want to think about is the GMM, the maximum specific gravity, at the initial gyration. So again, we can find out the value from the experiments and enter different asphalt binder, and then we're going to use the line to feed to the results, to the observed data, and we're going to find out the GMM at 4%, 4.7%. So with that, the value is around 87.1% for the blend 3. And so by doing that, we can then summarize everything. We can summarize the result for the blend 3, and we find that at the asphalt binder, the asphalt contents will be 4.7%, and with the air void of 4%, VMA 13.2%, VFA 70%, dust proportion 0.9, and the GMM 87.1. And then we're going to check this criterion. So air void is 4%, is satisfied, and VMA higher than 13% is also satisfied. VFA is between 65 to 75%. Is also satisfied, and the dust proportion between 0.6 and 1.2, and GMM less than 89%. So all these criteria are satisfied. Then we can claim that this one, this is the blend 3. Isn't a good design for the asphalt binder and aggregates, and it could be used for the SUPERPAVE mix design. So that's the third step, to check whether the blend, the selected aggregate structure within the estimated binder contents is appropriate for the SUPERPAVE mix design. And with that, we have selected the asphalt binder, we have selected the aggregate structures. Then the next thing we need to do is to do some sensitivity analysis about the specimen with respect to the moisture. So this one is can be conducted based on the standard test, which is defined by Asphalt test 283, and the moisture sensitivity is applied to. In this test, we're going to measure the moisture sensitivity, and we're going to use this one to measure the specimen under the proposed aggregate blend and the asphalt content. So the figure here actually shows the general requirement for the test, and I'm going to show you more details about the selections of the samples, the tensile strength applied, and also the moisture contents. So first of all, in this test, we will need to prepare 6 specimens, and they will use the designed asphalt structure and asphalt binder contents, and they will this will be selected from the previous 3 steps, and the air voids will be made around 6 to 8%. And for these 3 specimen, for these 6 specimen, 3 specimen are vacuum saturated with 90% of the saturation, minimal saturations, And we will also apply the freeze-thaw cycles to understand the first heat effect. And we will then apply some indirect tension to the specimen so that we can determine the indirect tensile strength for all the 6 specimens for the dry samples, for the samples with certain moistures, and for the samples experiencing the freeze-thaw effect. And then we're going to determine the percentage of the retention strength for the samples. So this would be the very brief procedure to conduct the moisture sensitivity analysis with the test 283 procedure. And so in the test, we will put 3 of them with certain moisture. Usually that will be around 55 to 80%, and we will leave the other 3 as the dry sample. And then we will try to check the short-term aging effect. The losing sample will be placed at an oven for 60 degrees for about 60 hours, and the compact mixture will be put in the oven for 3 to 4 days at 25 degrees. And then, of course, one is the dry sample, the other one is the wet sample, and they will have the exactly the same percentage of the air voids. And the next thing we're going to do is applying the vacuum saturation. So to do that, we will place the specimen in the vacuum chamber, which will be covered with at least 1 inch of the water. And then drop the pressure by 26 inches of the mercury for 30 minutes. With that, we will then tape the chamber to dislodge taped bubbles, and then release the vacuum and leave the sample in the water for 30 minutes. So this is the procedure for us to do the vacuum saturation. And then after the 30 minutes, we're going to determine the percentage of the saturation. So this equation, the equation below, shows the way for us to calculate the saturation. Basically, it will be 100 times D minus A divided by C minus B times E. So here A is the dry weight, is the weight without any water, and B is the weight in the water before saturation. And C is the SSD. It's called the saturation, the dry weight before vacuum. And the D is the SSD weight after the vacuum, and E is the percentage of the air void in the specimen. So you need to measure all these values for the whole experiment, and then you can calculate the percentage of the saturation. And that's the first thing we need to do. The next thing we have to work is the apply the freeze-thaw cycles to the sample. So basically, you need to put these 3 samples in the cold environment with a temperature less than 18 degrees for 16 hours, and then put them in the hot water, soak it in the hot water. The temperature is set at 60 degrees for 24 hours. This is, of course, this is only applied for the wet sample. And then we're going to apply the indirect, try to measure the indirect tensile strength, which would be estimated by this equation. So we have the specimen. We're going to apply the load to the side of the specimen, and then we're going to try to check the measure the tensile strength, indirect tensile strength based on the shape of the specimen. So here you have the diameters of the specimen, and you have the height of the specimen, and with that you can calculate the indirect tensile strength. in the moisture sensitive analysis, we will actually try to apply the tensile strength for the at the temperature of 25 degrees, and they will be applied for both dry samples and wet samples, and then we're going to check the average dry tensile strength and the wet tensile strength. We want to make sure that the ratio between the wet and dry tensile strength is higher than 80%. So this is the one requirement for the moisture sensitivity analysis. I guess I cannot finish the rest of the lecture, so I will just stop here. And if you have any questions about this lecture, just feel free to let me know. And we will finish all the rest of the contents about the Asphalt technology in the next lecture. And also in next lecture, we will have the review about the midterm. And I also plan to have a quiz at the end of the next lecture. So you will have some ideas about what we can do, what information you need to know for the SUPERPAVE mix design. Okay, do you have any questions for now? If no, yes.
I had a quick question about on Avenue, there's no folders in the assignments tab right now for us to upload the labs.
Okay, so it's you want to, okay. I will generate in the folder. Probably I did not forgot to make it visible. I will try to check that so that you can find out the folder after the class. Thank you for the notification. Okay, I guess that will be all today. If we don't have any questions, I will close the meeting today, and I will see you tomorrow. Thank you very much for your time, and I will see you tomorrow afternoon.